Now suppose we have a circuit that is composed of a capacitor and an inductor, and let's imagine that we have an open switch, and let's let at time equals 0 C is well let's write it like this: the potential across the capacitor is equal to some set value. And remember that C is equal to Q over potential. So at t equals 0, what that would imply is that epsilon naught is equal to the total amount of charge that we have in the system divided by C. Okay? So we have this, and when I immediately flip the switch, and for example, let's say that our plates are charged like this, so I close the switch, and what this will do is the negative charges on my plates here are going to try and flow through the circuit to get to the positive plates over here, and that will create a current. But as the current flows through the inductor, the inductor will create a back EMF, and that back EMF will oppose the direction of the newly established current, and it will then work to drive the charge back to its original configuration. So how can we see this? Well, Kirchhoff's rule would say that the potential at all times across the capacitor must equal the potential across the inductor, and if I say that the potential across the capacitor is equal to, at any given time, so Q is a function of t, at a generic time, Q of t over C is going to equal negative L di dt. But remember that I is equal to dq dt. So di dt is the same thing as d squared q dt squared. So we have q of t C is equal to negative L d squared q dt squared. And I'm going to write this in a slightly more suggestive form. Divide both sides by negative L. I'm going to get negative 1 over LC is equal to Q of T. And now this has a form of Hooke's law. So remember that Hooke's law looks like this, and this was the same thing as this. The second derivative of a function with respect to time is equal to a constant times that function. Okay? And what that gives us is the solutions to this were oscillatory, and x as a position of time, or x as a function of time rather, was equal to an amplitude times cosine of omega t. You could have a time or a phase constant in there, but the point is that omega was equal to the square root of k over m. So your angular frequency was equal to the square root of this leading constant. Well, this equation has the exact same form, complete with the negative sign. And so what we've found is the second derivative of my charge with respect to time is equal to a negative sign times a constant times my function of charge. So this is the same thing as acceleration is equal to a constant times x. And so the solutions for the charge as a function of time are going to be the maximum amount of charge times cosine of omega t plus a phase constant. And if we start our stopwatch right at 0, where the plates on the capacitor are fully charged, then the phase constant can go to 0, and we can say that the solutions to this problem are going to be the initial amount of charge on the plates times cosine omega t, where omega, or the angular frequency, is equal to the square root of 1 over LC. So the frequency would be 1 over 2 pi times 1 over LC, and the amount of time it takes for this cycle to complete would be 2 pi square root LC. Okay? So what is this telling us? Right? What is this telling us? What this is telling us is that let's actually use, let's use green for the current. Okay? So I have these electrons on this plate, and I have protons on this plate at t equals 0, and the electrons are going to flow, and so it's not like all of the electrons here are going to flow through and deposit themselves up here. The establishment of the potential means that the electrons that are free everywhere in the wire are going to move, and the electrons that are closest to the plates, the positive plates, are then going to be pushed onto the plates, and the negative charges here are going to be pushed off. So these negative charges are going to move here. The negative charges here are going to be pushed onto the plates. And so your plates are going to discharge fairly rapidly, but that produces a back EMF through the inductor. And so then the electrons reverse their direction, because now the inductor has induced an oppositely directed electric field due to an oppositely produced potential. And so that draws the negative charges back this way and pushes the charges that have been drawn off of this plate back onto the plate, and your situation reverses course. Okay? And then the situation is back to where it was at t equals 0, and the exact opposite phenomenon occurs. Your electrons that are here will get pushed off, and the electrons that can flow closest to the plates will flow onto the plates, and your electrons everywhere will be flowing. And then when the plate has charged this way, it will induce, or the induced electric field will pull them back this way, and your charges will just oscillate. Okay? The current will just keep switching directions. And this is a hint of AC current. Okay? This is a hint of AC current. But that is what will happen, and it happens because of the oscillatory solutions to this differential equation. Okay, so that is oscillations in the the LC circuit.